Actually, I had some issue with the internet. That's why I connected a bit late. 1 second, I will see if this screen is visible, right?
Yeah, screen is visible. It's not very audible. I mean, the volume is little low.
Or is it not audible?
Hello, hello. Can you call me later? Yeah.
Okay. Screen is visible now, right?
Yeah, yeah. It is visible now.
Okay, so I had actually the internet issue, so that's
Yeah,
why it was a bit late.
it
So
happens at times.
yeah. So in this session, actually, I will try to summarize what we have read
Okay.
during these weeks. So if I don't think someone else will join, so we can just directly start.
Yeah, yeah.
So, so we basically had the sessions. 1 second. Okay, second. Okay. So first we started with the diodes. The you had done those assignments, right, on the diodes. So we started with the diodes. Let's have a brief summary what we read about diodes. So basically, we started with 1 second. Conductors, semiconductors. So what are actually the semiconductors? So we can have brief discussion about the semiconductors. So you know semiconductors, right?
Yeah, yeah.
All the devices which we studied in this course are related to semiconductors. What about their conductivity? What is the conductivity? Because we have three things, right? One is
Yeah.
conductors,
Insulators.
semiconductors, and insulators. So we can say that the conductivity of semiconductors is in between conductors and insulators, right?
Yeah.
So can you tell me about the band gaps if you have studied about the band gaps? So if you have an insulator, if this is EC, conduction band, this is valence band, and if this, what is this called as? EC minus EV. What is this EC minus EV? This is called as band gap, right? AG.
Yeah.
So if this EG is very large, then we call when then we say that that material is insulator.
Insulator.
Okay. And for metals, let's say this is a Fermi level. And for metals, there is a Fermi level, and all other bands below this Fermi level are filled. Okay. So there is no band gap in conductors. Now, what about semiconductors? In semiconductors, what about semiconductors? The band gap is small, but there is some band gap, right?
Yes.
So that means the conduction will be there Because in insulators we say that there is no conduction, right? So this Eg is smaller than that of insulators. Okay.
Yes. Yes.
So now what? Give me an example of semiconductor. Silicon, right?
Silicon, silicon, yes.
Okay. The silicon has a band gap of more than I don't know the exact number. It's around 1 electron volt, greater than 1 electron volt. Okay. So if this is a Fermi level, now how we use this in our applications? And for that we start with, because if this is the, and one more thing, let's first study that. The semiconductors are now two types, based on
Intrinsic,
doping.
reciprocal, yes.
So what are the, one second,
Intrinsic and extrinsic.
right?
Yeah.
Intrinsic
Extrinsic.
and extrinsic. Okay. So what is the difference? What is an intrinsic semiconductor? No intentional doping, right?
Mm.
So if I take a silicon atom, what is the valency of silicon atom? 4, right?
Yeah.
And there will be another silicon atom here. So what is this bond? Covalent bond, right? So this is how, this is the atomic arrangement in the crystal. Okay.
Yeah.
Similarly, you can have another one famous that is known to almost everyone is germanium, right? That has a
Germanium.
lesser band gap than silicon. Now, what is extrinsic? Extrinsic is doped semiconductor, right?
Yeah, yeah.
So you have this silicon configuration. Now we do the doping, right? What are the two types of doping? You must have studied somewhere. It's P type,
P type and N type. Yeah.
E type, and N type, right? A P type doping
P
is,
type is holes.
yeah, this is
N type
holes.
is electrons.
This is electrons. So what does that mean? Its holes and its electrons.
The charge.
1 second. Okay. So what is p-type doping? So we saw that this was a silicon atom, right?
Yeah.
Now you take a p-type dopant. Dopant means a material which is used to dope this
Yes.
semiconductor, right? So let's say we take aluminum. Okay, what is the valency for aluminum? 3 plus,
Yeah.
right?
Yeah.
So that means it has 3 electrons in its outermost shell, right? So what happens is when you dope this material, it will replace some atom, this silicon atom.
Mm.
So this is silicon, and now instead of this silicon, second one, we have aluminum. But what are the number of electrons in its outermost shell? 3. Okay. So what is left is one less electron, right?
Yeah. Yeah.
So there was this electron here. So now once you replace this silicon atom, you divide this material by one electron. Okay. So that's why this absence of electron, this absence of electron is called as hole. Okay.
Yeah.
So now this was a p-type doping. What about n-type doping? Again, I will draw two silicon atoms. What will happen in n-type doping? You have n-type dopant, right?
Yeah.
That is the fifth group in periodic table, right? Let's say we dope it with phosphorus. Okay. So phosphorus has 5 electrons in it in its outermost shell. So what will happen is this silicon, and now comes the phosphorus, which replaces the another silicon atom. These are 4 electrons that gets bonded. But what about the fifth electron that remains in the material? So there are extra electrons now. So that's why it's called as n-type, and the other one was p-type. So basically what happens is in one type of doping, one electron due to replacement of one atom, there is a lesser electron, one less electron, and similarly by this there is a one additional electron. So that makes your device extrinsic and of the type of p-type or n-type. Okay.
Yeah.
So this was basically now about this doping. Okay, so this we just studied. Okay, so yes, now extrinsic is p-type and n-type is semiconductors, and p-type holes are in majority and in n-type electrons are in majority, right?
Yeah.
So this is now the band diagram. Do you know the band diagrams?
Yeah.
So here, if I just draw intrinsic SC, this is a band diagram of intrinsic semiconductors. So can you tell me what will be n-type semiconductor band diagram? Can you tell me? So I will again draw. This is EC. This is EV. Where will the Fermi level lie in the n-type semiconductor? Let me just draw the EI as well. You see that in the intrinsic EI and EF overlap, what happens in n-type? So to remember this, how anti-band diagram looks like is you have this EF near EC, and similarly for P-type you have EF near EV.
Yeah.
Okay, the more EF is close to EC, the more the device has electrons, and similarly, more it is closer to EV, the device has more number of holes.
Goes.
Okay, so this is a basic look of the band diagram for n-type and p-type materials. So if this is understood, we can move on to the p-n junction. Alright,
Yeah.
what is a p-n junction? What is a p-n junction? From the definition, it says it is the junction of p
Again, enter.
and n. That is, you have a material like this, and this is a junction, and this is p, this is n. We just studied what is p and n.
Yeah.
This contains holes in majority, this contains electrons in majority.
Yeah.
Now you know that if I have a if I have this water tank here and I have this water tank here. Now once they are separated, let's say these are separated, nothing will happen, right?
Yeah.
So once I try to connect them, let's say I try to connect them like this, what will happen?
The water will flow from top to bottom.
From top to bottom, right?
Yeah.
From here. Reason B, this is at higher potential, let's say, and this is at lower
Yeah.
potential. Or we can say that this material finds a space in this material. Okay. Similarly, now you see here, these are electrons here in this material. You have electrons. Now I will give you a material here which has no electron. What will happen? Electrons will flow,
Yeah.
right?
Yeah.
Without any external force, electrons will flow to this material. What is this process called as?
Conduction.
Diffusion, right?
Diffusion.
Okay, you must have seen once you when you use a deodorant, what happens? You just use a deodorant, then smell diffuses, right?
Yeah.
The
That's right.
same thing happens here. It finds a space here, right? So these electrons will flow. Similarly here, you see holes are in
Concentration
majority.
gradient.
Yeah, concentration gradient. So electrons are in majority here. So
Yeah.
what will happen? These electrons will flow here and holes will try to flow here, right?
That's
Because
right.
because of the, as clearly said, concentration gradient, right?
Mm.
So but till now, till but there should be a limit, right? They can't unconditionally move. They cannot move unconditionally, right? So can you tell me what happens? You have a silicon atom here in this region which has a hole, and you have a silicon atom here which has extra number of electrons. Sorry, yeah.
Recombination will occur, sir.
So this is actually basically an aluminum atom here, and this will be a phosphor. Due to this phosphorus doping, it anti-doping. So what happens is we
What
denote
that,
its
sir?
doping as Na and its doping as Nd, right? So
Yeah.
what will happen is this electron will come and occupy this hole. So what will happen? Before that, this material was neutral. Now this has a negative charge, right? We denote it by Na negative. Okay. Similarly, this was by single electron. Multiple electrons will flow. Similarly, holes will go in this direction. And once hole will flow here, it will occupy this electron and it will give it a positive charge. So what happens is in the diode, you have this junction. There will build up a charge like this, right?
Yeah.
So once you have this charge, you have an electric field in this direction, right?
Yeah.
Correct.
Yeah.
So now further, before we must have thought that these electrons can flow unconditionally to the left side, but now there is an inbuilt field which restricts the flow of electrons to the left side. Similarly, opposes the flow of holes to the right side. What is this called as? Built-in potential, right?
That is due to immobile charges, no, sir.
Immobile charges, right?
Yeah.
So this is a built-in potential. So now if I tell you to draw a band diagram of PN junction, can you draw?
Sir, sir, sir,
Hmm.
sir, this week's power amplifiers will discuss, sir. I mean, class A, B, that one.
Actually, this week we decided to summarize whole course what we have studied. You didn't join, I think, the last session, and before that, you had told me to discuss the questions. I discussed that, but you didn't join that session.
Sir, actually, that live session is cancelled, sir. After that, I am not free, sir. That's why.
Okay,
You discuss the problem, sir. I mean, I will go through the recorded lecture. No problem.
okay, okay.
You will discuss the problem, sir.
No, no, not today. Actually, we will focus on all the sessions we have gone through from the past weeks. So it is actually a summary week because this is the last week.
Yes, sir.
Okay, you can. I have, I think, the notes of the classes of the amplifiers. If you just give me a mail, you can just mail me. You must have my mail.
Yes,
Oh,
sir.
we don't have your mail, sir.
Okay, you have my mail.
No, sir. I mean, through that recording sessions, we can find on there in
You
slides.
can. You can remind me. You can remind me, and yeah, you can just find from that also. Uh,
Or else, could you please type your mail in the chat box, sir? I mean, I will be in touch with you.
uh-huh.
Okay.
Fine. Thank you, sir. Means I will be in touch with you.
Okay, I will send you those notes on classes of amplifiers. I have just handwritten notes.
Yes, sir. It will cover assignment questions as well, no, sir?
Um, that depends on the time if I will get the time.
Yeah,
So
yes,
if you
sir.
have any doubts, you can just ask on the phone. Do you ask the questions on the phone?
Yes, sir. Means if you go, means I am appearing for the final exam also, sir. It is very important for me. That's why.
Okay, I will check. Actually, if you had joined the previous sessions, you could have just told me because we were already lagging behind. We were only at the frequency response. We studied frequency response in the last session. So there are further 2 weeks before we could go to week 12 actually.
Oh, okay.
Hmm. So no problem. You will be able to solve the questions. I will just try to send you the notes.
Okay, sir.
Okay.
Sir, if you have any doubts specifically, I will be in touch with you, sir. Please help me, sir.
Okay. Sure. Sure. Sure.
Because I am appearing the final exam as well. That's why.
Which final exam?
It is going to happen on the 28th.
Oh, what year? Semester exam or?
No, sir. This course exam only.
Okay.
Another
So
is
the other
conducting
other
exam.
TA has the other TA not discussed. Actually, what I tried to do is I
Actually,
didn't want.
other TA yesterday's class is scheduled, sir, but due to I don't know that class is cancelled and it is scheduled at rescheduled at tomorrow, sir.
Okay, you can just join the set. Actually, what I tried to do is that I didn't want it to the repetition because I don't want to discuss the same questions which the other TA discussed, or because the same course has been given to both, right? So I tried
Okay.
to have some difference so that you may be able to gather knowledge from both the sessions.
Yes, sir.
That's why sometimes I try to just. focus on physics, basic physics of the devices as well, because that is not discussed in these courses.
Yes, sir. Yes, sir.
Okay.
Okay, sir. If I have any doubt, please help me, sir.
Yeah, sure, sure. So, okay, so about the PN junction, can you draw the band diagram of the PN junction? I will just draw here. This is same material. Similarly. So now tell me what is the band diagram of PN junction? This is P-type material, this is N-type material. Now you have to join them. And once you join them, what happens is the Fermi level, I will just make it easy for you guys. The Fermi level becomes constant. Okay? You cannot have different Fermi level on the both sides of the region unless you have applied a potential. If the device is in equilibrium, that means there is no current flow from P to N. Once the device is in equilibrium, EF will be constant throughout. So now I have drawn the EF. You just have to draw other energy levels.
Sir, are you waiting for any response?
Yeah, yeah, yes, yes.
Means, can you repeat? I mean, Fermi level is there. Okay.
You just have to connect these two. Fermi level is constant. Now you have to draw the band diagram.
For PN junction bed, right?
Yes, yes.
Sir, it should be Fermi level should be near to the valency band, away from the conduction band. Because of the PN junction diode, it is a forward bias. If it is forward
No, no,
bias.
not forward bias. So, okay. Uh, let's say this is the depletion region part. Forget about it. So, how should a P type look like? Like the above I have shown here. This is how a P type should look like, right?
Yes, sir. It will be near to the valency band.
So, it should be near to the valence band. And this should be your EC, right? This is your depletion region, okay? So, and on the N side, EF should be
Yes, sir. Near to the conduction band. Oh, PN, no, sir.
right,
Oh, yes. Yes, yes, yes. Correct.
okay. And now you have to just connect these, okay. This is how your PN junction. band diagram looks like. Okay,
Yeah.
and electric field. Electric field is always in direction of increasing energy level. So where is the increasing energy level? From this side to this side. So in this region, you will find that electric field is in this direction. Like we like we saw in the previous diagram, like when we had the build up of positive charge here and negative charge here on the N side, P side, right? We had this. Electrons, these are holes. Okay, so this is the band diagram of PN junction, and this total energy difference from this EC to this EC, this energy difference, let's say energy difference is E, and I multiply it with QE, that will give me potential, right? That potential is, sorry, not, oh, I did wrong here. Energy difference, let's say this is delta E by Q, will give me, this will be a built-in potential. Okay,
Yeah.
now if I apply a forward bias, what will happen during the forward bias? This is a question.
Sir, sir. Sir,
Yes, yes.
sir, could you please discuss? I mean, many times I will get confused regarding the band diagram in accumulation mode, depletion mode.
Oh, so
Uh,
that is a MOSFET. So we are not
yeah,
discussing MOSFET. We're discussing PN junction.
yes, sir. If possible, could you, that means, could you give? I mean, say, if you are studying, that will also be comfortable for you. That's why I'm saying.
We will discuss in this session a little bit about that as well. Don't worry.
Yes, sir. Means every time I will get confused whenever. That's
Yeah, sure. So tell me first about this. I just asked you a question. This is a built-in potential. Now I
yes,
apply a forward bias. What will happen? Just look in this diagram here. Look in this diagram. I apply here positive. Here it is negative. So now this is electric field like this, and external electric field will be from this direction. Second. Can you see the arrow?
yes, sir. Yes.
This. Okay. So obviously this should be in forward bias case, the built-in potential reduces, so it should be VBI minus V applied, right?
Yes, sir.
So what happens is once you apply this voltage, this potential reduces and current flows.
Current flows in opposite direction, sir.
Current flows from the, yeah, conventional current flows in this direction only, from right to left. Okay, so this is basics related to PN junction. Any questions?
No, sir.
So, one second, what happened? 1 second. Okay, so we discussed this. This is the diagram which I was talking about. Once you once these come close, this will be VBI potential. And once you apply a forward bias from this to this electric field, external electric field will be in this direction. And now these electrons will find an external field such that these electrons will pass from n side to p side. Okay. Similarly, what will happen in the reverse bias? See here. Now you have negative potential here, positive potential here. It will aid this electric field, right? It will increase this electric field and it will limit the current passing through the device. And if we talk about the ideal case of the forward biased diode, it acts as a short circuit. And if we talk about the non-ideal, then there is always a resistance in series, which is always a normal case. Okay. Now, do you know the definition of voltage source and current source?
Yes, sir.
So look here in this diagram. Uh, 1 second. Let me just note it down here. Current source and voltage source. Current source means current should remain. 1 second. Let me write. Current what will happen in the voltage source? Oh no, this is bad. So what did I just mention? Current
Infinite current, sir.
should know why infinite current.
Instead, ideal case, no?
No, current
Resistance
should
should
remain.
be very high.
Yeah, resistance should be high, not current. Similarly, here voltage should remain constant. Ideally, actually, yeah. This is the ideal case. So what does that mean? If I have to plot ID, sorry, not ID, IV characteristics of this current source, how should it be?
It should be vertical, sir.
I should remain parallel to V. I mean, to the
Parallel to
axis.
V, right?
Axis,
It should
X
be like,
axis.
yes, it should be like this.
Oh,
Okay. Similarly, IV voltage source
Parallel to I.
parallel to axis.
parallel to Y axis, right?
Yeah.
Now, can you tell me a diode is diode a voltage source or a current source? The question is diode a voltage source or current source?
Voltage source, sir. Means my reasoning is because of the cut in voltage only it will conduct in non-ideal case. So I came to conclusion it is a voltage source.
Then
Repeat,
is it
repeat.
a voltage source?
Yes, sir.
So let me just write first the answer from answers. You're saying that diode is a
Voltage source, because of the cut in voltage only it will operate. If it is less than the cut in voltage it won't be operate, it won't be in a conduction state.
no, that is different reasoning. Conduction, it is conducting or not. I can say that we have current only after V in. So that is not the definition of voltage source. Voltage source is voltage should remain ideally constant, right? Across a device. That you just saw that is the operation of diode, that it will start conducting after a particular voltage. That is correct, but that is how the device operates. The question is how it will act as a voltage source. Can you draw on your paper IV characteristics of diode?
Sir,
Hmm.
uh, is there any follow up, sir? Yes, I didn't get that.
So
This voltage.
did you draw the IV characteristics of diode?
Yes, sir. Under
One
a cut
second.
in voltage it will
One
be
second.
parallel to the current.
Hmm. So this is like this, right?
Yeah.
Sir.
This is your diode characteristics.
Yes, sir.
So you can extrapolate this voltage. This is called your cut-in voltage, right?
And
So you will see that you go on increasing your voltage, external applied voltage. You go on increasing this voltage, but you see that across a diode there is a constant potential, which is called as this voltage. So this is the definition of voltage source, right?
yeah.
Because across a diode there will remain a constant voltage. Now, if I had some device which has IV characteristics like this, So what will be your definition for this device? So you go on increasing voltage,
Current is constant, sir.
current is constant. This is a saturation current. This is a current source, right?
Hmm.
Okay, so this is a definition. You see from this slide as well, we have this saturation current. We model it as a current source. Okay, I hope the definition for voltage source and current source is clear.
Yeah.
Uh-huh. Okay. So now
Just
let's.
tell me one thing. Can I ask you something, sir?
Yeah, yeah, please.
Now, this curve, what we are drawing, I mean, the saturation part of it, is
Uh-huh.
it going to remain parallel to x-axis continuously, or is going to have some inclination?
That depends on the type of device you are using, and if you use a long channel device, usually this behavior is a MOSFET behavior.
Yeah, yeah,
We will discuss it. So for now, you can say that if the device is long, there is no channel length modulation, then this device characteristics will remain almost constant. But in short channel devices, that means when length is less, then this bias dependence, there is a channel length modulation due to this bias, right? So what happens is, let me just draw it briefly. Initially, if L is long, L minus delta L is not that significant. So current almost remains constant. This delta L is dependent on VD. But if this channel L is small, then L minus delta L becomes effective, right?
yeah.
And as VD increases, delta L increases, L minus delta L will reduce. And once it reduces, current increases. So in short channel devices, what happens is this is not constant, this almost increases. We will discuss it in the channel modulation part if there is something in the slide, or we can discuss it still. Okay, so this is a channel modulation effect. The current may increase depending on the CLM in the device. Okay, so let's move. So now next is in the semiconductors we discussed MOSFET. Here I have just shown the three terminals. We may have body terminal as well. Let's focus on three terminals here. So this is a basic schematic of MOSFET. Okay, so what is this type of MOSFET? Is the N channel MOSFET or P channel MOSFET?
Say in channel,
N channel. Why?
because substrate is P and source and drain are N.
Okay, so that means when you apply the voltage, create a you will create a channel here that will be of electrons, right?
Yep.
Right. So
Yeah,
we
yeah.
have three regions of operation with the MOSFETs: accumulation, depletion or weak inversion, and strong inversion. What is accumulation?
Means
Conduction, non-conduction
inverse of
region.
the inverse of if it is a P channel, sir, we'll apply negative. If it is a N channel, we'll apply positive. Inverse of
Accumulation means this is P well, right? So this has
yes, sir.
holes. If these holes accumulate at this region, this is called as accumulation. This will happen when gate is negative biased. Okay, so for negative voltages, the device will be in accumulation. Okay, and then when you go on increasing the bias, the device will slowly go into depletion, then weak inversion, and ultimately we will have a strong inversion. Strong inversion is when you have a high sheet charge density at the interface. Okay, here in this region. Alright? Accumulation will accumulate holes and strong inversion will have electrons. You can see here, as Vg is positive, electrons start to accumulate at the interface. Okay, and since P well, as I said, it is P-type doped, so there are holes. Once electrons start accumulating at the interface, these holes will occupy these electrons and the charge at the interface will turn into negative, right? So that's what happens in the depletion part. These Na P well, which contains holes, accumulate, capture these electrons and give a negative charge. So that is a depletion region. Okay, and after the depletion region, we further increase the positive bias. Then at that time we will get inversion. Okay, as is written here, at larger gate biases, electron in the interface is equivalent to hole concentration. So that is actually a definition of inversion. We usually say if there are 10 raised power 23 holes per cubic centimeter in P well, then we say that inversion occurs only if at the interface your electrons have the same concentration, that is 10 raised power 23 per cubic centimeter. Okay, and usually when we operate the device, we uh, keep the device in strong inversion. Okay, so you can see from his curve that it has almost a diode-like behavior. Similar VTH, it has a VTH, and once it is above VTH and in further VTH plus some voltage, your device will operate in the strong inversion part. So this is a basic definition of VTH. It is same as you draw the cut in this tangent, and you can just get a threshold voltage of the device. And again, as I said, the MOSFET operates as a current source. You know, by definition, IDS is given by this equation, right? You must remember this equation. It's a very important equation for solving all the questions. This is a normal equation which has all the parts from linear region to a saturation region. Okay, so in this region, this is not used in this region. Device is mostly used in the saturation region. You must remember that all the questions we did in the second part of the course, we always saw that the device was always in the saturation, right? So in this region, actually, the device is operated as in the switch. That is another application.
Triode.
Yeah, and this is usually for power amplifiers or amplifiers. Okay, or whatever your sources, you saw the differential amplifier, op amps, and all the normal common source amplifiers. You saw that the device was always in a saturation, and you must remember the formula for saturation is simply this times VGS minus VT whole square by 2, and this voltage, what is this voltage called as?
Threshold voltage.
Pinch off voltage, right?
Sir, could you please talk about the sub-threshold region also, sir?
Uh-huh. What?
Sub-threshold region. Sub-threshold.
Subthreshold we usually say in IDVG characteristics. So you have this device, you see that behavior in log scale. Subthreshold means below VTH region when the current is very low. That is mostly important for logic applications.
Sir, I have last few doubts, sir. One,
Huh? What?
for
Your voice is not audible.
sir, in order to decrease the power dissipation,
Yeah, your subthreshold slope, the subthreshold swing should be very less. Yes.
Yes, sir. Sir, but MOSFET will be won't be in operation, no, sir, because we need to maintain the VGS should be greater than the VDS should be VGS minus. Then only we can operate in saturation region. Can we operate one single stage amplifier in subthreshold region? Is it possible, sir?
No, why will you operate your transistor in, if you are going to for amplifier applications, then it won't amplify in subthreshold, right? There is no
Yes, sir.
gain. There won't be any gain in subthreshold region.
Yes, sir.
So you have to
Uh,
operate in subthreshold, in above subthreshold, in saturation. Yes,
yes, sir. One more,
because you
small
want
doubt,
to
sir.
reduce the nonlinear effects as well as your gain should be high. In subthreshold, your device is not actually completely on, right? This is a leakage
Yes.
currents.
Yes, sir. Yes, sir.
So
Sir,
what was your question?
sir, in single step means, sir, and previously in Cadence I designed a circuit, sir, through 180 nanometer technology. To what extent I can reduce the current with respect to width
Okay, your
height of
voice
both?
is there is some noise in the background. Can you be clear?
Yes. 1 minute, sir. 1 minute, sir. Sir, 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 for MOSFET, means I aim to design a, sorry, a single stage amplifier. To what extent I can reduce the power dissipation, like that I designed a circuit, sir. What my guide said, we can operate a MOSFET in a subthreshold region also, no? Do you know about this? Like that, question has occurred, sir.
You want to operate your device in subthreshold region.
Yes, sir. What I answer now, sir, we cannot operate. It means if you operate less than the threshold voltage,
No,
MOSFET
you
won't
want.
turn on, sir.
Hmm. You have to,
Won't turn on.
if you are designing an amplifier, then you should have your device in saturation. Because
Yes, sir.
if you go on in if you in fact if you keep your device near threshold, you will have very large amount of nonlinear effects, and due to those nonlinear effects you will have very less gain. So what is the aim of your amplifier? Your aim of the amplifier is to have gain, right? So you won't achieve that gain, so you have to operate in the saturation.
Yes, sir. Yes, sir. I understand. Sir, means to what extent I can, with respect to current, with respect to technology, note to what extent I can reduce the current. That only is the only possible. Yeah?
To what extent you want to reduce the current? I don't get your point.
No, sir. Power dissipation is nothing but VDD into that is current.
Uh-huh.
No, sir.
Yes,
That
yes.
current for technology node, if I analytically it is possible, sir, to what extent. But a technology node, only if you, if I keep on decreasing few currents, that width is not showing, sir. 180 nanometer technology.
So
To what
base
extent?
you can reduce your current by reducing your VG, right?
Yes, sir.
You can reduce as much as you want, but your specification, that is the final output, that is your gain, right? You what is the
Yes,
final
sir.
out? What is the final goal of your project? Gain, right?
Yes, sir. Yes, sir.
Your gain should be, let's say, 15 dB, 16 dB, and for a particular frequency range, right?
Yes, sir.
You are operating over a frequency range. You can tune you can tune your configuration. You can lower your VG, but keeping the device on, obviously, and you
Yes,
can
sir.
lower
Means
your
by
VG.
keeping the MOSFET everything in a saturation. Yes, sir.
You can reduce the VG. Okay, you can reduce the VG. You can increase the VD. That will keep the
Mm.
device in saturation, and
Mm.
you can go on decreasing, but you should not affect your it should not affect your final goal. So you have to
Yes, sir.
optimize your, for example, you can connect in the cascode, not cascode, cascade. You can connect the multiple stages in the cascade to increase the gain. Okay, and by not from the single transistor, you can use multiple transistors at lower current levels to actually get the final output that will give you the desired gain. Uh,
You do familiarize with cadence, sir?
huh?
Do you familiarize with cadence, sir? Cadence software.
Cadence? No, I have not used Cadence. Cadence is, I think, cadence is a simple where you use the circuit elements, right?
Yes, sir.
You use the PDK, that is your 180 nanometer PDK, right?
Yes, sir. Yes, sir.
You have to just connect the transistors, okay? And
I
then
know. I mean, sir, GMID methodology is there, no, sir. I am not
GM
getting
GM
GM over ID methodology is there, no, sir.
GM methodology. If, come again.
GM versus GM by ID methodology, sir.
GM by ID methodology. GM by ID methodology. No, I don't remember such thing. What is that? You can just tell me. Maybe I will be able to tell you further.
No, sir. Means mean it will give
Actually, when you characterize a device, you have to first characterize the GM, right?
yes, sir.
You find the GM. What is the GM of the device?
Yes, sir. Means it is little bit for sir. Means I will mail you, sir. Means we'll talk.
Yeah, sure, sure.
I will be in touch.
Sure. Okay, so this was the basics related to this, and then we studied this. Okay, so what is pinch off actually? How does it happen? You have this MOSFET, you have this channel, right? These are electrons. Okay, so what happens is go on increasing VD. Okay, this is N type, right? And this is P type. So this is a PN junction. And once you reverse bias a PN junction, the depletion width increases, right? So similarly, same thing happens here. It gets depleted. And once it gets depleted, the channel becomes some sort of like this. Okay. This is delta L, that what I was talking about. This is L. And you know ID is mu n Cox W by 2L VGS minus VTH whole square. Now this is not L actually, this is L minus delta L. This length gets reduced. So pinch off is the voltage. No. Okay. Pinch off is voltage at which the channel pinches off. That means if it was your gate, source, drain, like this voltage, okay, at which the channel starts pinching off. And after that, this is your VP, IDVD. After that, the current remains constant. And once you further increase this VD, if it happens that the channel is short, this pinch off point goes like this. This is a delta L, and this current will start increasing like this with VT. That is a channel length modulation, and we see this channel length modulation only in short channel devices. In long channel devices, L minus delta L is not that effective. All right. And if we see from the we just talked about the three regions of operation of the MOSFET. If we see from the capacitance characteristics, it acts like this. It is this region is accumulation region, and then this capacitance go on reducing to the C depletion, and after that you have again increase in capacitance due to increase in the inversion charge, right? And this is your subthreshold characteristics in the log scale, and similarly, and this portion is strong inversion portion. And this and keep in mind that this characteristics is only for the low frequency regions. In high frequency regions, you will find capacitance of this type, high frequency. Okay. Any questions on this capacitance curve? All
Yes, sir.
right.
So could
Yeah.
you please explain about little bit more, sir?
Okay.
Come.
So the device is majority is holes, right? So when the
Yes, sir.
holes are in majority and you apply negative voltage, then they can interact with your external bias, external AC voltage. So this is MOSFET. One second. So if this is gate, this is oxide, and this is your P valve. Okay. Now this has majority holes. Now, no matter what voltage you apply, these holes will always interact with. This is a gate bias DC plus small Vg AC. This is how you obtain the capacitance characteristics. Let's say my device is in accumulation. Accumulation, now you know accumulation is when you apply a deep negative voltage, right?
Yes, sir.
This is your Vg. So Vg is negative. What will happen? The device is in accumulation. And I told you this is gate, then this is oxide, and then this is P well. P well is holes. This acts as a parallel plate capacitor with dielectric oxide. Okay. So what is the capacitance of a parallel plate capacitor? If this is the oxide between it, distance is T
You
of
also. Yes.
multiplied by area, right?
Yes, sir.
So this is the capacitance. Same thing happens here. You have the C ox dash. That is a capacitor. We usually draw it in capacitance per unit area. But this is only till this has a majority holes. But once you go on decreasing this Vg, not decreasing, sorry, increasing. You go on increasing now in this direction. What will happen? This capacitance starts reducing till depletion. Why? This is a C dip. Because this is not only a single capacitor, but you have here P valve. This is source, drain. There will be depletion as well, right? And then after depletion, there will be inversion. Now till here, what happens is this is not only a single capacitor, but it is C ox in series with C depletion. So what is the total capacitance? C ox, C depletion divided by C ox plus C depletion, right? So that's why what happens is once you go on increasing this bias, the C depletion comes in the picture, which is very less than Cox. So you know that this relation will always give you the answer that is less in magnitude, right? So C depletion is less in magnitude, so C depletion will reduce the total capacitance. What happens after that? The electrons come in the picture. You go on increasing the Vg, electrons start coming, and you have this inversion part. And then after a particular voltage, this becomes again constant, and please remember that these are almost equal. C inversion is equal to Cox. This happens in MOSFETs, but if there is a MOSFET, what is a MOSFET? MOSFET is similar, same, but without source drain contacts. And for that, that is a frequency dependent. For higher frequencies, you will get a characteristics of this kind. Okay, is this clear?
Yes, sir. Sir, I mean, so generally I will get out, sir. Whenever it will from accumulation to depletion mode, it will decrease, no, sir. Is there any
Hmm.
limit
What?
from in accumulation mode, it is constant, no, sir.
Mm-hmm.
In depletion mode, it is decreasing, no.
Total capacitance will decrease, right?
Yes, sir. Means is there any limit? Is there any identification from where to where it is decreasing? Means the transition is happening from.
Here, you
Uh,
can see the transition, right?
Yes, sir. Means, is there any formula like that? Any questions based on that?
Usually, what you get in these in the capacitance characters, what you get the extraction type of questions. What I mean by the extraction type questions, like find P-ox, find doping, like this. For example, I will give you this characteristic, right? And I will give you a total capacitance of 1 picofarad here, and let's say this is zero point 0.1 picofarad. Okay, so I will tell you find the T-ox. How will you find the T-ox?
Based on
Yes.
COX, we can find now.
Yeah, this is 1 picofarad is epsilon ox by T-ox. You know epsilon ox for the silicon. Let's say this is the silicon. Epsilon ox, you have the
2.85.
value. Yeah, you can just find the T-ox. Once you find the T-ox, then you go to this part. Now you go to this part. This is C total. C total is C ox C depth divided by C ox plus C depth. Now you know the C total, that is zero point 0.1, and you know the C ox, right? Now only factor is C depth. How you find C depth?
Yes, sir.
C depth is from uh, you will get it from the depletion width formula. Depletion width formula is mm, as far as I remember, it is 2q epsilon. No, no, 1 second. It is. I
2
don't
epsilon by Q by
remember.
1 by NA plus
Yeah,
1 by ND into
yeah.
negative potential.
2 epsilon n doping by qn. Sorry, not q. It's potential by qn, right? This is, I think, the formula for the
Yes,
X
sir.
depth. From this formula, you can just directly calculate the capacitance. Not capacitance, you can calculate the Q depth, depletion charge. Depletion charge, as far as I remember, is 2Q epsilon n
Into W, sir.
into W, 2Q psi s. I have to check. This needs you can check it on your own as well, or you can give me a moment. I will just check. One second. One second. Oh, that copy is not with me. I need to check the formula, but it is like this only. You have a definition for CDEP as well, and from that you can just directly calculate the doping and all. So in these kind of questions, these are mostly the extraction type of questions. Okay, and then again you have the C inversion. Most important is you have to use this region to extract the device or process parameters. Yes, please. You are muted. You can unmute yourself. Hello. Do you have any question?
Hello,
Uh,
sir. Can I ask you something?
yes, yes.
Yeah, sir. Actually, we are solving the problem. The problem we're having the two-stage amplifier. Uh, that is, a cascaded one, where the
Uh-huh.
output of the first stage will be going to the given to the input.
Okay.
Uh,
What is
One
the
of the
question?
problem we have solved is having the capacitor in between
What?
into the uh, output of the first and drain of the second.
Okay. Let me just draw. This is a one
Yeah, this
one
is the
MOSFET.
first stage you can say. This is second stage.
Mm-hmm.
The output the first is cascaded to the second to gain the multiplication of the gains to have a higher gain at the output.
Mm-hmm. Like this.
Yes, sir.
Mm-hmm.
Now there is
Then
a capacitance, a capacitor connected between the two. That is VDD, I mean the drain of the second and gate of the second.
like this.
C1 to, yeah, is a capacitor like this. Now
Okay.
this capacitor is, since it is common for the gate and drain, it has to be divided by the Miller's theorem. Correct, sir?
Yeah. Yeah.
So now theorems, somehow I'm not very clear about it because we
You.
yeah. So then there is the output capacitance also,
Hmm.
correct?
Yes. Like
Which
this.
is, yeah, sir, yeah. So now these capacitors are divided. I understand that C out, I mean the one which is at the output of the second stage is
Mm-hmm.
almost same as the C, almost same as the capacitor in between. I mean the CC or no
Oh,
C1.
okay. One. Repeat. What?
Shall I
Repeat.
continue, sir?
Yeah. Yeah. Repeat. Once you use the Miller theorem, then what?
Yeah, because what and the second side you have to, if you have the capacitor to be considered for the
Mm-hmm.
input side, say of the output of the first stage, then it
Mm-hmm.
has the gain coming in between, correct? It
Mm-hmm.
multiplied by the gain.
One second. You just have to use V output here, right?
Yeah, V
So,
out of the first stage. Yeah,
yeah, whatever is V output that gets applied here, that is the input voltage for this.
that's right. Yeah, sir. Yes, sir.
Okay.
Now, these capacitors going to be divided, calculated, and then the output capacitors, capacitor and input capacitor. The first stage will
Hmm.
be, rather than the second stage, not first stage, second stage will be calculated. The second stage, we have the capacitor will have a gain in between. I mean, multiplied by the gain. Correct, sir?
Mm-hmm.
This side, I'm the left hand side.
Yeah,
Sir,
both.
sorry
Yeah.
for interrupting, sir.
What
Sir,
is?
sir, I have a class, sir. I'm left.
Okay,
I
okay.
will reach out to you through mail, sir.
Sure.
Yes, sir.
Yeah, continue.
Sir, if I want to calculate the output impedance of the circuit,
Mm-hmm.
looking at from the output side,
Yes.
then I have to consider what all I have to consider. That's basically my question is all about, sir. Because suppose your first stage you have a GM1 as a transconductor and GM2 as a transconductor on second stage. and
Mm-hmm.
then we have this capacitor. I mean, this capacitor got divided, and
Mm-hmm.
suppose I want to divide, separate the poles, because if I want to keep a distance between the two poles, I have to introduce new capacitance in between, parallel to this CC, what you call the coupling capacitance parallel to this,
CC, wire
to
is CC?
separate out the poles, or rather to increase the distance between the poles,
Mm-hmm.
parallel to that CC, whatever you said, CF, whatever is there.
Okay. So what is the
Because
question basically?
uh, sir, pole is 1 upon RC, correct, sir?
Mm-hmm.
So R1 C1 R2 C2. But normally for the stabilization of the system, we should have R2 C2 upon R1 C1 should be greater than 1.
Okay.
So, sir, how my point was, sir, I got many a time confused between how to calculate the output capacitance, because output capacitance, if you look it from the output side, and say you have
Mm-hmm. No,
RD
no,
at the RD1 and
no.
RD2 at the, say, the drain part of the circuit.
Output capacitance will be simply this one. If already there is some other capacitance here connected, CL
So that
something
get
is,
added up.
yeah, that will be simply CL plus this Miller capacitance. That is simple like this. I don't, please check the formula if it is
Yeah,
1
the
minus.
formula is okay, sir. Formula I
Okay,
can check it out. I
okay,
just want
so,
to get the clarity on the subject, sir.
okay, so output capacitance will be simply like this. That you don't have to use that
No, but
for
what?
process.
Yes, sir. No, no, I'm talking the output impedance, not
Okay,
the capacitance, sir.
okay, so now
So,
once you know down the capacitance, output capacitance, then is remains is output impedance. Output impedance you have to calculate from here, right?
yeah, output impedance from the output side, they're having the
Hmm.
GM2, GM1, R2,
But
R1,
remember,
R2,
remember
R1
that.
are the
Just
uh,
remember that.
resistances.
Remember that you are calculating time constant for this capacitor, right?
Yeah,
And at that time, you don't have to consider these capacitors.
okay.
Like I
But
said,
answer, sorry,
like
sir,
I,
in the answers, they have considered these capacitors,
uh,
except GM1, that is transconductors of the first stage from the
mm-hmm.
MOSFET. We have considered all
Oh,
the parameters R2,
okay.
R1,
Okay, so
C1, C2, all the things, sir.
is the question, okay, maybe, okay, so they have not used I guess that method, then maybe they have, what they have done is they have calculated total output impedance.
Yeah,
Okay, the goal is you have to calculate poles, right?
yeah. Poles I have to. My idea was to separate out the poles, so that I will the system will be stable, and that unity gain, the unity frequency gain will be lie in between the two
Hmm.
poles.
Hmm. Okay, so you can use directly if they have used the total output impedance, it consists of these parts as well. You can directly looking into here, connect positive, negative, Vx, Ix, right?
Yeah.
So this
Yes,
is your,
source.
let's say this is C in. So this is 0. So this is basically 0 here. This is ground. Current will be 0 if CLM is considered. So this will be CLM. And this will be C in. And this is like this. Now see here, I think. uh I think you should
because the output impedance they are given in the answer is having all the parameters except GM1, that the transconductance of the
Well, yes, that
state.
is zero actually. It is zero, so that won't be there.
They are considered R1, that is a diode, sorry, drain resistance and a diode, rather drain circuit, as well as R1, R2, GM1, I'm
So
sorry,
this is
GM2,
actually like this. This
yeah,
is
yeah,
CF, right?
that's right, yeah, yeah,
So
capacity in
that
between.
they have not used Miller capacitance there.
Miller, they
Uh,
used it because they had divided this, because otherwise they won't able to consider. I mean, they are divided into the two parts, that the input side and output side,
so
and they added with this.
that's the question. If they use this, then you see here this will be simply CF times 1 minus A, right?
Hmm.
Hmm. But there won't be voltage in here, right? It will be zero. So at that time, your output impedance will be simply R naught. So I think you should keep it connected and calculate the output impedance.
Perhaps I may not able to explain you proper. I will show you the diagram. I send you the diagram. I
Yeah,
mean,
you
so
show
that
me
will
the.
give a more clear picture. It's slightly my side, maybe there is some shortfall to explain you the things. So that will
Hmm.
give more clarity, because otherwise it's okay. But point is, I'm not able to derive that equation, because sir, if you see from the
One
output side,
second, one second. Can you just tell me what is the equation?
uh,
R out, right? Z out.
in the Z out, yeah, Z out.
Okay, Z out.
Equation is pretty lengthy. It has a lot of denomination and numerator, denomination, and poles, and basically zeros. And there's a one pole, two zeros. Sorry, two poles, one zero.
No,
So
you
it
can
is,
just tell me what is the. Do you have written somewhere?
sir. Actually, uh, it is having, as I said, it is cascaded one, cascaded in output. This one, but the
Mm-hmm.
point was, even Z out. Somehow I'm trying to calculate. It is not
Mm-hmm.
matching, because they only has all the parameters, all the values,
Mm-hmm.
except, as I said, GM1 is not there. GM2, R2, R1 capacitors at output, plus the Miller's capacitor
Mm-hmm.
at the output, which is got added, and the input side of the second stage, it is having the Miller part of the capacitor, and the input side is having the, sir, what do you call it, the gain part of it, and then
Uh-huh.
other R2 and other parameters, sir. I
Mm-hmm.
will show you. I will send you the diagram. That will, like, because it is slightly difficult.
Yeah, yeah. You can just send me that. I will get back to it. Sure. I think okay. So let's go through quickly what I have kept in the slides. Then we can. So this is basically okay. These are not the simple questions. You must have attended these sessions. And this is how you calculate R out. These were, I think you discussed it very well, right?
Yeah, that's right.
How you can calculate the output impedance, right? I told you to remember that formula as well, like this one, source resistance plus drain resistance and gain multiplied by that. I think, and then last was the frequency response. I hope that was also clear. If you have any doubts on it, I just gave you the my ID. You can just contact me and then we can discuss on it. Do you have any questions apart from any? How was the course and something like that? Because this was the last session. There won't be any sessions further. So if you have anything before we end this, because this course is completed.
Yeah.
So do you have anything that you want to mention before we end this meeting? If no, then I think we can close. If you
Yeah.
don't have, if you don't have any question. Okay, so best of luck for your exams if you are
Thanks.
prepared.
Thanks. Thanks for your time and guidance.
Yeah, thank you for attending the sessions. It gets difficult to sometimes to have no one in the sessions and talk with yourself.
Yeah, it's quite interactive, quite educative, quite informative. I appreciate that, sir. Thanks for your
Thank,
time.
thank you for joining. Hopefully we'll see each other in next semester.
Yeah.
Okay, okay, bye.
Thank you. Thank you, sir.
Thank you.